So we have one more panel for our conference today. This panel is on knowledge practices. So it's looking at the formal method and the epistemologies that go into artificial intelligence coming from different perspectives. And our first speaker is Evan Hepler Smith, who will be joining Duke University as an assistant professor this fall, right?
Thank you. Thank you all. Thanks so much for the opportunity to be here. I've learned an enormous amount, and I'm really excited to get to present a little bit of my work. I have all of the slides for this session posted on my website, which is here, in case there's anything you see. You need not transcribe. I wanted to start with this really wonderful line from the end of Jeff Bowker's Memory Practices in the Sciences. Just a wonderful book to come back to, I think, in light of some of the conversations we've been having. In the second to last-ish sentence of the book, Bowker writes, "If we want the future to be other than it seems to be turning out, we must create a past that is other than it seems to have turned out." So if we want a different future, maybe we should think about making a different past. And I think that's part of what we're up to here. I'm gonna start out really quickly by talking a bit about the history of science and the history of artificial intelligence, the subject of this session, part of it anyway. I'll move on to speaking a little bit about my work on the history of chemistry and the place of artificial intelligence or artificial intelligences in that. I'll speak just a bit about one particular project of mine that looks at the articulation of computational methods and non-computational methods, people methods in this field. And then I'll speak a bit at the end to something that's going to seem like a non sequitur, but isn't. So as our organizers wrote in the abstract for this session, historical epistemology and attention to practice have long been central concerns for historians of science. And I think three ways in which these things have been concerns for historians of science and might be concerns for historians of artificial intelligence as well are first in histories that situate universal knowledge in specific places, rhetorics, and practices. Second, attending to more kinds of activities, people, and practices as knowledge-making enterprises. And this is in science. We can think of the analog in artificial intelligence. And then third, in including, or maybe even starting from, histories of applied science, thinking of things that look like applications of science as instead the stuff of science of which we can tell the history. And we have papers that do each of these kinds of things for the history of artificial intelligence. In my talk today, I'm going to be focusing on the third, histories of applied artificial intelligence. I'm thinking here in particular with the work of the historian of science and historian of computing, Michael Mahoney, who in his 2005 article, The Histories of Computings, suggests that historians attend to specific communities and how they worked out specific hopes, expectations, difficulties, machines, and methods, different computings, paying attention to these diverse computings in the making and in how the communities that made them reshaped not only their own practice locally, but also computers and their adaptation by others more broadly. So can we do something like this for the history of AI? Doing so requires having some way of defining what a community of artificial intelligence might be. How do you circumscribe such a community? It's kind of fuzzy word, community. And one answer is suggested by the work of the historian of technology, Ann Johnson, who writes about what she terms knowledge communities. Communities centered on a particular engineering problem that Johnson terms an attractor, that bring together practitioners, maybe from diverse backgrounds and fields around that specific kind of concrete engineering problem. So onto chemicals. I work on the history of chemistry. Chemistry, like so many other fields, is being revolutionized by machine learning and big data. You can tell just by the terminology that this article is already out of date. They would say AI now, I guess. So enterprises like making drugs, making new materials are being made subject to the kinds of artificial intelligence tools whose development we've been discussing. This is about these things that we call chemicals or molecules, but you'll notice that these things on this screen are not actual physical powders or liquids, but rather diagrams, and the conflation of these particular really recognizable kind of schematic diagrams and materials that are out there in the world and in bodies is really central to my research. But the idea that the material practices of making and using these things have somehow been transformed into an informatic enterprise is, like so many other things, not new. The material science of chemistry has been becoming a third-order science of information since 1969, at least. And if we look a little bit farther back, chemists have been talking about the importance of information, of reference literature in print form since the early 20th century. You can find similar quotations going back to the late 19th century. And in fact, some of these printed resources have been retrospectively understood as one practitioner puts it, computerized collections waiting for a suitable computerized handling system to be discovered. So there's some sense among at least chemists working with chemical information in their research enterprises that chemistry was always already a computational science somehow. So that suggests that maybe there are some questions we can ask around how it became so, and what the specific problems in which this understanding of chemistry emerged were. We can look to examples of the development of artificial intelligence projects that were focused on chemistry. We've heard a little bit earlier today about the Stanford University Dendral project, which began in 1964. It was really originated by the molecular geneticist Joshua Lederberg at Stanford, who, among other things, was trying to develop instrumentation on a contract with NASA to hypothetically be put on an extraterrestrial satellite or explorer to do remote chemical analysis in the search for life. One can imagine the sorts of dual-use technologies that government funders might have been thinking about in doing remote analyses of living materials. But it was in Lederberg's collaboration with Ed Feigenbaum, along with chemist Carl Djerassi, that this early expert systems project, really strongly located within the domain of chemistry, analytical chemistry, came into being. Dendral, this program, illustrated as of the 1980s, the state of the art in automatic hypothesis formation. So this was an AI project, but really emerging out of a chemical problem. Chemistry also provided the context for some early work in machine translation. Michael Gordon, in his great book, Scientific Babble, has written a little bit about this. The information scientist Eugene Garfield, who's now better known for his development of citation analysis, citation indexing, wrote in his PhD thesis, or in an article based on his PhD thesis, that solving the problem of translating chemical nomenclature was going to be a crucial stepping stone towards developing more general natural language machine translation. So again, we have this project that seems like a big, broad, general AI project that's getting worked out in the particular context of chemistry. In fact, we can drill down even a little bit farther and find that for the practitioners involved in Dendral, involved in machine translation, or at least for Garfield and his efforts, there was a shared attractor, a shared kind of core problem animating some of these projects that might, more loosely be classified as applied artificial intelligence. In both of these cases, the core central problem was, as Lederberg put it, a formal representation of chemical graph structures, or as Garfield put it, generating accurate molecular formulas for chemical names that could also display and print ideographs, that is, structural diagrams. That is, the central problem for the members of both of these projects for what might seem to be artificial intelligence development or testing was actually a little bit different. It was translating chemical names into graphical chemical formulas and into machine readable notations. This problem, this attractor, was indeed of general interest for a community of, maybe about several dozen to 100 different scientists working in different national contexts in the Soviet Union, France, Britain, Germany, and elsewhere in the 1940s to the 1960s. It was a problem that had been the nucleus for the development of a new specialist professional cohort within the field of chemistry, chemical documentalists, chemical editors, documentation chemists, who spent their time in a way very much like that of women computers doing mathematical computation in the creative deployment of algorithms here to do this work of translating really, really complicated chemical structural formulas, these graphical formulas, into systematic names like delta-2-parazoline, 5,2-furol, and so on and so on and so forth. So we have a history of labor here associated with the development of this story as well. We can trace this story all the way back to 1892, the Geneva Nomenclature Congress, a meeting that I discussed in the beginning of the book manuscript I'm working on now, which is about the kind of history of this whole problem of translating chemical diagrams into chemical names. And what we find if we trace this problem back to its 1892 first articulation as such, is that at its core, it was about information management. What seems to be a problem of adequately representing the world turns out to be a problem of adequately representing the materials of the world for the purposes of organizing all of the information that chemists have produced about them, and specifically for the purposes of organizing chemical information to support research and development enterprises in the chemical industry to make lots and lots and lots and lots more of these kinds of chemicals. So we find that this attractor, formal representation of molecular structure, enabling mappings of diagrams to names to machine notations, is at the center of these applications of AI in chemistry. And one conclusion we can draw from this is that whereas recent surveys like that of Leo Breiman looking at two cultures of statistics, a culture associated with machine learning versus a culture associated with data models that assume that the world accords to a certain structure. These analyses that tend to characterize such data models as unrealistic and impractical might be corrected by, or might raise the question of why anybody thought that such a structured approach to the world would be adequate or useful in the first place. In fact, for these chemical communities of AI, precisely the problem they were facing, precisely the world that was in front of them, was already structured in what seemed to be an extraordinarily computationally tractable fashion. We can talk a little bit more about that. We can also talk a little bit more, if you'd like, in Q&A about this project in expert systems development that I've written about a bit in the field of synthetic chemistry, but I want to move on to my non sequitur that's not a non sequitur in conclusion. So if one way of telling the history of AI is pluralizing it in this fashion, looking at histories of AIs, looking to communities of applied AI, there's an ethical imperative as well as a sort of useful historical epistemological aspect to this as well. Some of you might be familiar with Joanna Radin's article, Digital Natives, winner of the Sigsis Prize recently that argues for inclusion of indigenous histories in studies of big data. There's another article that I really have found quite useful recently, Making Kin with the Machines from Journal of Design and Science, written by a group of indigenous scholars, talking about how contexts of application of AI technologies might be something that we might wish to kind of take quite seriously. Skipping down to the second quotation here, a problematic aspect of the current AI debate, the authors point out, is the assumption that AIs would be homogeneous. The country to which AI currently belongs excludes the multiplicity of epistemologies and ontologies that exist in the world. And approaching the relationship of humans to each other as well as to machines ethically, these authors suggest, and I'd like us to think about, might require reconsidering the ontological status of each of the parts which contribute to AI. That is, relations to AI might also be relations to whatever the machines that preceded AI or the practices that preceded AI, and might not ought to be differentiated so strongly from AI in the first place have been. Thank you.